Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be looking at the topic acid, bases, and salts. And we're going to be looking at the last bit of acids, bases, and salts. So today we are looking at water hardness. So we'll be looking at the differences between hard water and soft water. Now, in relation to um, uh, lathering. So, and then later on, you're going to categorize different types of hard water. So, water can be pure or impure. Pure water usually is a substance which is a compound of hydrogen and oxygen, and it boils at 100 degrees Celsius at sea level. So we know that this is the pure water from even the concepts that we learned in melting point and boiling point in Form 1. We know that pure water boils at 100 degrees Celsius, and it also melts at 0 degrees Celsius and has a density of 1 gram per centimeter cubed at sea level. And then impure water are natural waters constituted of dissolved solutes in pure water. So anything that dissolves in water makes that water to be impure. For example, if you take pure water and then you add some salt into it, it stops becoming pure water, it becomes impure. So hardness of water, this is water without dissolved substances, lathers easily with soap, so it refers to as soft water. That's how we are able to identify soft water. One of the ways we can identify is through lathering. When, for example, we are doing washing. So if you add soap in soft water, you notice it forms lather faster or quicker or easily. While if we add lather in hard water, it doesn't lather easily. Sometimes it doesn't lather at all, it just forms scum. We're going to discuss what that scum is. So let's look at an experiment to show the effect of water containing dissolved salts on a soap solution. So distilled water is placed in a conical flask, and then soap solution from a burette is added to the water and shaken. So if the soap fails to lather, more soap solution is added from the burette till it lathers, and the volume of soap required for lathering is recorded. So the procedure is repeated with each of the following. We have tap water, rainwater, dilute solutions of magnesium chloride, sodium chloride, calcium chloride, calcium nitrate, calcium sulfate, magnesium sulfate, magnesium hydrogen sulfate, calcium hydrogen carbonate, zinc sulfate, sodium hydrogen and potassium nitrate. So the procedure is repeated with these solutions and then they are boiled when boiled. So when this water, soap is added to these solutions first, and then these solutions are heated, or this water containing these dissolved salts are heated, and then the soap is added. So you notice that distilled water requires very little soap to reproduce lather because it lacks dissolved salt as termed as soft water. This is the water that we use in the lab that is distilled. We commonly use it because it doesn't have those dissolved salts and it's referred to as soft water. You notice that it lathers very easily. The one containing solutions containing sodium chloride, zinc sulfate, potassium nitrate, and sodium hydrogen carbonate do not require a lot of soap to form lather. And then solutions containing, and you can see these solutions, they have different cations. For the ones containing calcium ions and magnesium ions do not lather easily with soap. So the reason is because the soap reacts, the soap which is sodium stearate. We're going to discuss that later in organic 2. You can check that video out to form an insoluble salt of metal stearate called either magnesium or calcium stearate, which is generally referred to as scum. So if you look at the equation, you see how scum forms. So water that is containing calcium ions and magnesium ion doesn't lather. The reason why it doesn't lather is because it forms an insoluble salt with the soap. So instead of it just interacting with the soap well, it reacts with the calcium ions, and the magnesium ions react with the soap, and then they form a scum. or an insoluble salt. So if you look at the equation below, you can see the sodium stearate reacting with calcium. There is an interchange of cations so that it forms calcium stearate, which is now the scum and sodium. Same case happens with magnesium. So it reacts with the sodium stearate, and there is an interchange of cation to form magnesium stearate, which is a scum. So solutions containing calciums and magnesium, or the water containing calciums and magnesium, tells us that it's not soft water. So that's water with magnesium and calcium ions is termed as hard water and can only be made soft by removing these ions, upon which the water will lather easily. So if you have magnesium ions and calcium ions in water, you have hard water. So when calcium hydrogen carbonate and magnesium hydrogen carbonate are boiled, the amount of soap required to lather decreases than before boiling. So if we boil this water that contains the hydrogen carbonate and magnesium hydrogen carbonate, you notice that after boiling, the amount of soap that will be required so that it can lather decreases, meaning it can lather now easily after boiling. The reason why we boil, it helps to decompose the hydrogen carbonates to form carbonates, which precipitate out, leaving soft water which easily lathers. So you notice you're going to categorize this salt, which contains calcium hydrogen carbonate and magnesium hydrogen carbonate in a later on. So the amount of soap solution used in this solution containing sulfates and chlorides of calcium and magnesium do not change significantly even after boiling. So you see that you have two categories. We have the calcium, magnesium, the ones that contain hydrogen carbonate ions, and the ones now contain chlorides and sulfates. So this tells you these are two categories. So these ones, if you boil them, they do not like change their lathering. If they didn't lather initially, they are not going to lather even after boiling. So the soluble sulfates and chloride of magnesium do not decompose upon boiling, hence cannot be precipitated out. So there are usually two types of water hardness. Now, in relation to what we have just discussed on the experiment, we have the temporary hard water and permanent hard water. So temporary hardness is brought about by dissolved calcium hydrogen carbonate and magnesium hydrogen carbonate. You see the hydrogen carbonate ones. And then this is formed when rainwater dissolves the carbon dioxide from the air to form carbonic acid. This carbonic acid in turn passes through rocks and limestones, which react to form the soluble salt. For example, if carbonic acid reacts with limestone calcium carbonate, it forms calcium hydrogen carbonate. If it reacts with dolomite, carbonic acid reacts with magnesium carbonate to form magnesium hydrogen carbonate. Then there is another type of water hardness we call permanent water hardness or permanent hardness of water. It is caused by the presence of dissolved calcium sulfate and magnesium sulfate, and it's caused by water that dissolves calcium sulfate and magnesium sulfate from the ground. It is also caused by the presence of magnesium chloride and calcium chloride. So you notice we have the main cations, which is calcium ions and magnesium ions. And then these ones are now categorized in two types of anions. So we have the temporary hardness containing the carbonate ions, and then the permanent hardness containing the sulfate and the chloride ions. But you notice for both cases, the cations are the same. The anions are the ones that differ if a certain water is temporarily hard or permanently hard. And you noticed when we heated the calcium and magnesium ions containing the hydrogen carbonate, when you boiled them, they were able to lather easily. But for the ones that contained sulfates and chloride, when you boiled them, there was no change that happened. So you make sure you keep that in mind as well, especially when you're identifying the cations and anions contained in soft and hard water. So we'll do one question or two. So two samples of water, C and D, were boiled. When tested with drops of soap, sample D formed lather easily, while sample C did not. Name the possible salt that caused the hardness in sample D. So we have two samples of hard water. So we have already been told they are hard water. So you know they contain calcium ions and magnesium ions in them. So when they were tested in with drops of soap, they were boiled. So they were boiled first and then they are tested with drops of soap. So sample D formed lather easily while sample D did not. So the possible salts that caused D, it means this one is temporary hardness. We say temporary hardness is calcium, hydrogen carbonate, or magnesium hydrogen carbonate. And then the table below shows the number of drops of soap solution needed to lather with 10 centimeters cubed of water. So you see sample A only requires 5 drops to lather in cold water and 5 drops to lather in heated. So it doesn't change. So for sample B, it required 6 drops to lather, but when heated, when boiled, the number of drops reduces, meaning it lathers now easily. For C, it lathers very easily both in cold water and heated water because it's the same. So the first question, identify the anions likely to be in A and B. So A, we can see it's taking a lot of drops to lather, and even when it's heated, it still doesn't lather that much. So we'll say we have sulfate and chloride ions, and then B, which lathers easily when it's boiled, it means it's hydrogen carbonate ions. So that's it. So in the next lesson, you're going to be looking at ways of removing water hardness. So see you in the next lesson.